Hello and welcome to another LeetCode problem. Today we're going to be doing maximal network rank. So in this problem, you have an infrastructure of n cities with some number of roads connecting those cities. Each road indicates that there's a bidirectional road between cities A and B, and then the network rank of two different cities is defined as the total number of directly connected roads to either city. If a road is directly connected to both cities, it is only counted once. And so that's essentially we're trying to get the maximal network of all the cities. And so basically what they're asking is you want to find the two nodes that have the most roads connected to them, and then you want to return how many roads they have connected to them. So like in this example, if we have 0 and 1, so 0 has 2 roads connected to it, and 1 has 3 roads connected to it. But this is counted twice because it's connected between them. And so it's going to be 2 plus 3 minus 1, and it's going to be 4 because this one's counted twice, right? It's counted for 0 and for 1, and we only want to count it one time. So the way we count it one time is just subtract 1. Okay, now for the second example, the answers are 1 and 2. So let's take a look for 1 and 2. 1 has 1, 2, 3 nodes. Yeah, and 2 has 1, 2, 3 nodes as well. But they share a road here, so it's going to be 3 plus 3 minus 1. So essentially the answer is, or the answer of like the network rank of the two cities is the number of roads for A plus the number of roads for B minus 1 if A and B are connected. So A and connected to B. So it's actually pretty straightforward, and this connected thing is the thing that gives it some space, because if you didn't need to know if they were connected, it would be really easy. Like you would just go through the roads and you would just count the integrity for every single road, and you could just return the top 2. I guess you could probably still kind of do something like that, which would make it a little bit faster, right? Like you could just sort the keys or something. But either way, the constraints here are so small that we know we can do whatever we want pretty much and make it work. So we're going to have a reasonably efficient solution here, and let's figure that out, right? So essentially, we're given these roads. So because we're given these roads, this problem is fairly straightforward. All we have to do is, when we're given these roads, all we have to do is make a hash map. And in the hash map, the key is going to be the road, or not the road, it's going to be the n value, like the city. And the value is going to be the set of cities it is connected to, right? So once we have that, and it's pretty straightforward to do this, right? So for every single road, we're just going to say like, okay, like let's just actually, what we're going to focus on in this problem is kind of like how to fill out this hash map, and then the rest of it's going to be pretty straightforward. So let's actually copy, let's actually work on like this part right here. Like how do we set up this hash map, right? So we're going to just do this. Yeah. So essentially we're going to go through these roads and we're going to set up this hash map. Okay, so let's do that. So we're going to start with this road right over here. And let's actually, maybe we can even write them out to make it easier. Okay, so let's just say we have 0, 1, and we have 1, 2, and then we have 2, 3, and 2, 4, 5, 6, 7. Okay, so this is our array. Now we can get rid of pretty much all of this. And now let's just go through what we would do, right? So we have this array, and let's look at our hash map. So 0, 1 means there's a row between 0 and 1. So essentially for our hash map, we're going to have key 0, and it's going to have a set. So we'll just say like this is the set, and it's going to have 1 now in here. And then for 1, I'm not going to have the closed parenthesis because I'm going to keep adding to it, but essentially it does have a closed parenthesis. So for 1, we're going to add the 0. Okay, now for the second one, there's a row between 1 and 2, so we're going to add this 2. So for 1, we're going to add 2, and then for 2, we're going to add 1. And 2 and 3, so we're going to have a 3 here. For 2, we're going to add 3. For 3, we're going to add 2. 2 and 4, so we're going to add 4. For 4, we're going to add 2. For us, this is 3. This we're going to add 4 here. Okay, 5 and 6, so 5, 6. And we don't need to store like the number of connections because we can just get that from the length of the set, right? So for 5, we're going to have 6. For 6, we're going to have 5. And yeah, our constraints are so small, we can definitely do something like this. Okay, and then 5, 7. So 7. 7's going to have a 5, 5's going to have a 7. Now we can actually close all these up. So close this, close this, close this. Okay. And now all we do if we compare cities, like let's just say we compare 0 and 1, we're going to say, okay, let's take the number of edges. Let's take the length of the set for 0 and 1, so that's going to be 1 plus 2 if we're comparing these two. And are they connected? And the way to check if they're connected, we could just check, like, is 1 in the set for 0? Yes, it is. So if it is, let's subtract 1. And essentially that's all you're doing. So if you can connect like 3 and 5, you would say, okay, let's just take the length of 3 and length of 5, 1 plus 2. Are they connected? No, they're not. 3 isn't in 5, and 5 isn't in 3. And so that's your answer. So essentially, you just loop through all possible combos, and you just get the biggest answer, and that's pretty much it. So it's a pretty straightforward problem once you understand what you're doing. So literally just make a set for every single city, and then loop through the cities, and it's like an n squared, loop through the cities and compare to every other city, and just get the max there. Okay, so now we have enough to be coding. So first thing is we're going to create we want to create a hash map with all of these numbers. So we could just say like counts equals, and we're going to say I key, and then the value is going to be a set for I in range n, right? We just want to make a hash map with all the cities, so it'll be 0 to n, and then they're all going to have an empty set. Now we're going to go through roads, so we're going to say for, let's just say like first, second, in roads. We want to add these counts, right? So it's going to be counts first dot add second, pretty straightforward. Counts second dot add first, also pretty straightforward. Let's actually fix our tabbing here. And so now essentially we have these sets for every single city. It's going to have a set of every city it's connected to. Now let's make our result. Okay, so now let's set the result equal to 0 here. And then we're just simply going to go through all of the possibilities. So we're going to say for I in range, this is n, right? Because you have n numbers. For j in range I plus 1, because we don't want duplicates. I'm going to say count equals, this is going to be length of counts I plus length of counts j, the length of each set. And then we're going to say if counts, or this is I in counts j, we could check either one would work because they'd both be in the other set. We can say count one, probably a terrible name for this count situation, but that's okay. Get res equals max res and count, and let's return the result and see what happens here. We don't have any errors. We might though. Okay, valid syntax. Return. Okay. Okay, let's take a look. I haven't seen that one before. Okay, so you can see it's reasonably efficient. And yeah, let's think of the time and space here. Okay, so for the time, let's think what it is. So we're making a set. That's just whatever. We're going through every single road that is let's just call this like maybe edges or something, E. And then here we are comparing every single vertex. So this is going to be like plus v squared. Because if this is a vertex and this is an edge, to make this, you have to, this is going to be length E, and then this is going to be length of the vertex. So it's something like this. Obviously one is way more likely to be bigger than the other, right? Like it depends though. But yeah, this is probably likely to be bigger, so maybe you could say this gets canceled out. Okay, now for the space. So what are we storing? So we are storing, for every single vertex, we are storing every other vertex that it can be connected to. So worst case scenario, it's almost all connected. So I think it's something like v squared-ish is going to be the space here, I believe. Because yeah, like let's say everything is almost connected. You know, you can't have like duplicate paths, but I think it's something along v squared for this actual hash table. But like I said, because the constraints are so low, it's only 100. It's like 10,000, so it's nowhere close to anything bad. There might be a more efficient way to do this without using like v squared space. I'm not entirely sure, but I kind of just went with this solution because it's pretty straightforward and your constraints are so easy. Okay, but yeah, that's going to be all for this video. Hopefully you liked it. If you did, please like the video and please subscribe to the channel. So thanks for watching.